Here's the good news about the remaining chapters we're going to cover. I think all of them that we'll get to are basically review and small extensions of things you would have done last year in your Algebra 2 course. So everything we're doing from here on out should feel pretty familiar, which is great, right? So this first chapter we're going to look at is going to be about exponential, logistic, and logarithmic functions. We talked last year about logarithmic and exponential functions. We didn't talk about logistic. It's not a big deal. They're pretty easy to deal with. They're not much different. But in my experience, as somebody that's taught that Algebra 2 course for a long time, one of the least sticky subject areas is this idea of logarithms. So it'll be a good to go back and revisit this topic here now, right?
Mr. Coolidge, I have a suspicion that I'm going to come back from spring break and forget all this.
Yeah, that's why I'm not so worried. It's only one section. It's like the introductory section, so it's not that big of a deal.
I'm just telling you that. I'm just being honest.
You know what? I appreciate your honesty.
He's going to change his lesson plan.
No, I'm just telling him. I'm just hoping that he picks up what I'm throwing down.
Oh, okay.
So we're going to start here by talking about exponential functions. So exponential functions can be written in the form f of x equals a times b to the x, where a is not 0, b is positive, and not equal to 1. So that's kind of like a lot of criteria there. Why do you suppose we don't allow a to be 0? What would happen if a was 0? It just all zeroes out, right? So you're left with just y equals 0, which is a constant function. That's a type of linear function. We don't want to include something like that, okay? What would happen if b was equal to 1? You'd have b to the x, or 1 to the x is 1, and 1 times a is just a, which again, constant function. That's not exponential. We don't want to include that. What about, though, what would happen if b was negative? What's the problem there? Why aren't we wanting to include negative values? So why would the negative number potentially, or negative base, be a problem with the exponent? What exponents would be a particular problem? Not squares. No. What, the what? Not to the first. Fractional exponents. Specifically, things like 1/2, 1/4, 1/6. Why are those a problem? Those are the same thing as radicals, even radicals, which we know if we take the even root of a negative number, you get an imaginary result. So you'd have something with like discontinuities all over the place. It would be just like a gigantic mess, like really ill-behaving. Not something that we want to call exponential either. Is everybody okay with that? Okay. So an exponential function is like continuous everywhere. It does have a horizontal asymptote at y equals 0. As a little bit of vocab here, the a we often call as the initial value. And the reason we call it that is, in most contexts, x equals 0 would be like the first input for something. And if I do f of 0, what does that simplify down to? Well, b to the 0 is 1. Why is that the case? Remember, anything other than 0 to the 0 power is 1, right? 0 to the 0 is undefined. Yeah, it's one of those indeterminate forms. It actually has, like, depending on how you look at it, could have multiple different correct answers, which is why we call it undefined, because it doesn't have a single value. So f of 0 is just going to be a, right? That's why we call it the initial value. Does that feel okay, guys? And b we call the base of the exponential. So just a little bit of vocab there, and just kind of explaining some of the criteria. The big thing to remember here, though, is the criteria for b, that b has to be positive and not equal to 1. Cool so far? No big deal, right? Just some definitions. Okay. So let's say we want to evaluate some values for f of x is equal to negative 2 times 4 to the x. So let's start here. First things first, negative 2 times 4 to the x. Can I just write that as negative 8 to the x? Heck no, right? Remember the way that we multiply numbers is if the bases are the same. We can multiply them together by keeping the base and adding the exponents. Or if the exponents are the same, we can multiply the bases together and keep the exponent, right? Those are just rules of exponents. I'm going to kind of review those things as we go, and I'll kind of write them off to the side in blue to justify things that we're doing. But those are just some basic rules for exponents, right? So if you want to multiply two numbers together, either the bases have to be the same, base stays the same, exponents add, or if the exponents are the same, we multiply the bases and keep the exponent. Cool? Okay. All right, so if I want to do f of 2, well, that really just means I'm plugging 2 in for x. Order of operations says, what should I do first? The exponent. So 4 squared is 16. So 2 times 16 is negative, or negative 2 times 16 is negative 32. So that's that. No biggie, right? F of 0 is, should be able to do this quick in your head, negative 2. Very good. Why is that? Yeah, basically like we explained before with the initial value, right? Everybody's cool? What about f of negative 3? What does a negative exponent do again? Makes a reciprocal. Very good. So that's going to be the same thing as 1 over 4 to the third. 4 to the third is 64. So I have negative 1 over 32. So again, the property there is of exponents that we used there was that. You're seeing that these stupid evaluate problems that we're doing right now is nothing more than an excuse for Mr. Kulik to review some of these properties of exponents. which again, ideally you would have all remembered from last year, but I know things fade, and that's the point of like doing it again. Because at this point you're like, why are we just doing these stupid computations? Basically just as an excuse to review these properties. All right, f of -2, I'm sorry, 1/2, not -2, you dummy. Okay, what does a fractional exponent mean? Yeah, so this one means a square root. The property that we're using there is that one. And then our last example that I got here, f of -3/2. Okay, so the trick I would use here is that -3/2 is the same thing as like -3 times 1/2. Everybody's okay with that idea? And we know that an exponent of an exponent is multiplication. So that's what I'm going to use here to make this a little bit easier to deal with. So that's the way I'm going to think about it. Now it becomes pretty trivial. To take care of. Everybody's cool? Again, all of these things were stuff you could just type in your calculator, right? The point of this, though, wasn't to get the right number. The point of it was just to kind of review these properties of exponents, because it's been a minute since we've had to use these on a regular basis. Hi, how are you?
Good, how are you?
Just fine. Thank you. Aria, it's for you. Okay. So let's look at another example of a different kind of problem. Let me pull this up. It'll just be easier to copy and paste these things. There we go. All right, so let's say that we have a problem like this. So we have some values in a table, and we want to write the exponential function for this table. So we want to write an equation of the form g of x equals a times b to the x. Everybody's cool with the idea? So we need to figure out the values for a and b. There's a hard way to do this, and then there's, in some cases, a really easy way to do this, depending on what points you're given. Now, this set of points, we can do it the easy way. Aiden?
Can you get an a value by g is 3?
Yeah, so the key here is if we have the x-coordinate 0, that's automatically going to give us the a value. Very good. Everybody's cool with that? And then I can take any other point and use that to solve for b. I would use the point 1, 15, because it makes solving for b much easier when the exponent on the b is 1. How do you guys feel on that? Pretty easy, right? No big deal. Where's my mouse at? All right, let's look at another example. Here, there's really no way to deal with the shortcut, right? Because we don't have an x-coordinate 0. We're still going to be looking to do the same thing, but what we're going to have to do this time is to create a system of 2 equations. So we're going to use one point to write one equation and the other point to write the other equation. I'll refer to those equations as A and B. If you think back to last year, we solved systems last year. What were some of the ways that we learned how to solve systems algebraically? Substitution. What was the other one? Elimination. Either one of those two is appropriate here. Personally, I like to use elimination in this situation. Now, last year when we solved systems using substitution elimination, the variables were always being added or subtracted. So when we used elimination, we're just going to be adding or subtracting the 2 equations to eliminate things. Here, our variables are being multiplied. So to do elimination this time, we're going to be dividing. Usually what I like to do is the equation whose exponent is bigger, I like to make the numerator of my division problem because it makes the solving a little bit simpler later on. But it's still possible if you do it the reverse. It just makes it a little bit extra work for you. Yes? Sure. In doing it this way, we just basically are going to ensure that we don't have, or we'll have less fractions to deal with. So when I divide the left-hand sides, I have 12 divided by 48. When we divide the right-hand sides, I have a times b to the -1 over a times b to the -3. Well, 12 divided by 48 is just 1/4. The a's are going to cancel. That's the elimination happening. And then b to the -1st divided by b to the -3rd is going to be b to the -2, or sorry, b to the 2. Again, remember that the property of exponents we're using here is that when we divide exponents, we subtract. Everybody feel good so far? Okay. So to get the b squared by it, or the b by itself, I have to square root both sides. Remember, when I square root both sides of an equation, I make a plus or minus. But in this case, what can I say?
Yes, he agrees.
I know that because b is the base of an exponential, it must be positive. So I can just forget about the plus or minus. And there's my value for b. Now that I have this, I can plug this back into one of my two equations. I'm going to plug it into equation b. So I get a equals 6. So that then is everything I need to write my exponential equation. You guys feel okay there? No big deal, right? A little bit trickier than the other one because you have that system to solve, but it's not a hard system. You can always just divide one by the other and the a's will automatically drop out and you're just left solving for b. They can all be done the same way. It really doesn't make much difference. Okay. So when we have some exponential equation and we want to compare it, say two exponential equations together, it's often difficult to do that because if the values of b are different, they're going to behave very differently, right? So one thing that we're going to be interested in doing is going to be finding a way to rewrite exponential equations so that they have the same base, so they're easier to compare. If we're looking to do that, the obvious first question is, okay, we want to rewrite them so they have the same base. What base should we pick? One of the most common bases is this natural base, also referred to as Eulers number. So the symbol we use to represent that number is the letter E. This letter E is equal to the limit as x approaches infinity of 1 plus 1 over x to the x, which is about 2.7182818, yada, yada, yada. This is a big, long, irrational number. Remember, what does irrational mean? Okay, it's infinite, doesn't repeat, but the real definition is that it can't be written as a fraction, right? That's really what we mean by that. But yes, that's equivalent statement saying that it's doesn't end and it doesn't repeat. You know, there's no repeating pattern to it. And this Eulers number seems like an odd thing, like, okay, like why this? It turns out that this number kind of pops up unexpectedly a lot in natural phenomena. So it's, we'll look at a little bit later kind of where the inspiration for like doing this comes from. But we'll do that a little bit later. So now what we have is an exponential function f of x equals a times b to the x, can be written in the form f of x equals a times e to the kx. So that's just an alternate form. So every exponential we can rewrite as a times e to the kx, which makes it a little bit easier to compare two exponential functions. What's the takeaway between looking at these two? really that b has to be equal to e to the k then. Does everybody kind of see that? And we'll talk about how to do that conversion later. We're just simply stating at this point that we can do this. We haven't discussed how to do it yet, and that's okay. We'll get to that a little bit later, but right now we're just focused on that this is possible to do. Everybody cool? Okay. So we have two different ways that we can write an exponential function. Really, we classify these exponential functions into two types. So we call these guys growth and decay. So if we have the classical definition of an exponential, if the a is greater than 0 and the b is greater than 1, that's growth. And if the a is greater than 0 and the b is between 0 and 1, that's going to be decay. And if we have this new version of our exponential, if the a is greater than 0 and the k is positive, that's going to be growth. And if the a is greater than 0 and the k is negative, that would be the decay. I guess I should have made one other piece up here. We should state that for that other version of the exponential, that again, a can't be 0 and k can't be 0. I think that probably goes without saying, but I'm going to say it anyways because let's just be specific, you know? Why can't those be 0? Because they just end up into a constant function if we allow them to be 0, right? Same kind of reason we went over before, which was why it was kind of obvious, but I'm going to state it anyways, right? Just to be specific. Now, what would happen if the a is negative? It's just that the criteria flip. Okay. Let's do some more examples. So given that the population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? Well, when I read this, I really break this up into two separate questions. The first question is just going to be to write an exponential model to describe that situation. And the second part of the question will be solving that exponential model when the population is 1 million. We kind of see that? Now, if I look at this initially, it's like, okay, I need to write some exponential function, and I'm given points. Oops. that look like this, right? Everybody kind of agree that that appears to be kind of the starting piece. Now, what's the bummer about this when we look at it this way? Is that I'd have to solve a system to end up doing this, right? So here where we have the year, well, let's write it this way. X equals the year, and f of x is our population. Mr. Kulik would rather avoid having to solve the system because he can do this in a clever way that allows us to not have to solve a system. So rather than thinking about this as f of x equals a times b to the x, I'm going to think about it as f of t, where t is going to be the years after 1990. So when I do that, the first point becomes 0, 782, 248. And the second point would become 10, 895, 193. And you can see, hopefully, the big advantage here is that because the x-coordinate here is 0, I get the a value strictly for free. Is everybody okay with what I've done here? I wrote a lot of stuff out because I want to, like, this not to feel like some super sneaky trick that I'm doing. So to solve for the b then, I'd have this. Everybody cool? So to solve for b, the next thing I do is, good, just divide by that 782,000 and change. Okay, and then how do I get rid of the 10th power there on the b? A 10th root, right? And because that's an even root, I get a plus or minus, but it's a b value, so I don't really get that. So I'm going to go ahead and type that into my calculator then. As a reminder, the way we do this, to get a 10th root on your calculator, I'm going to type the number 10. Then I'm going to press the math button and choose command number 5. And then I can just, that gives me a 10th root. And I can type it in otherwise. What's the other option you can do instead of doing a 10th root? You could do the exponent 1 over 10. Yep. Okay, so what do we have here? 1.013578108 is about my value for b. So my function then, f of t, is going to equal 782,248 times 1.013578108 to the t. So like that was all doing the first part. To solve the second part now, I'm going to plug 1 million in for my population and solve this for t. Everybody's cool there? Now, if I were to try to do this algebraically, what am I going to have to use along the way? Since the exponent, or since the variable's in my exponent, I know I'm going to have to use at some point a logarithm. Have we talked about logs yet? No. So am I going to try to solve this algebraically right now? No. What am I going to do instead? I'm going to graph this. Yeah, exactly right. So I'm going to go to my y equals menu. The left-hand side, I'm going to graph in y1. The right-hand side, I'm going to graph into y2. And I'm actually going to do a little sneaky trick here. Rather than copying this whole number down, I'm going to just store this as a variable. I'm going to store it as the letter A. That way I don't have to type all that stuff into my calculator. And additionally, it's going to be a more accurate answer because not only does it store the number that's displayed, but it stores also all 99 decimal points that the calculator has in its like cached memory. So I'm going to have like the most accurate possible answer here. Is everybody cool with why I did it that way? Okay. So then I'm going to reset my window because I have to think about this a little bit carefully. So the X here is really representing the years after 1990. So at X equals 0, that's 1990. At X equals 10, I'm going to be I've gone up about 100,000 in population. So I would guess at X equals 20 or so, I'm going to be right around my target of 1 million. I'm going to overestimate that. I'm going to go all the way up to 30 because I would just assume not have to come back and double check things again, like to extend my window if I underestimate it a little bit. My Y's are representing the population. The smallest population I care about is this 782,000, but I'm just going to type in the round number of 750,000. And the biggest population I care about is 1 million. But I'm going to, again, write that a little bit over. I'm going to do 1 1/4 because I want to be able to see the intersection there pretty clearly. But that should be good. Let's go ahead and hit graph now. Here's my line at 1 million. Here's my population curve. I'm interested in that intersection right there. How do I find an intersection on a graph? Second trace. We'll open up the calculate menu and I want command intersect, which is command 5. Since there's only 2 curves that I'm graphing and there's only 1 intersection, I can just ignore the questions and press enter 3 times, which gives me about 18.2 for T. Okay. But does that actually answer the question that I'm being asked in the problem? So it's asking me, in what year will the population reach 1 million people? So how should I answer that then? So I'm adding 1990. So I would say during the year 2019. Or, I'm sorry, 18. Is everybody okay with that? Oh, 2008, sorry, yeah. Arithmetic is hard, guys. We did all the hard part, and then I boogered adding 1990 plus 18. It happens sometimes. What do you guys think? Is that okay? Not a big deal, right? Not too bad. Question though, does an exponential model seem like the most appropriate way to describe this population growth? So like, let's say, okay, maybe 200 years in the future, maybe at New Boise, at 20 or 2,200, right? According to my model, my population is going to be 13 million or something. Does that seem reasonable? The city going from 700,000 people to 13 million people? Why not? I saw some head shaking. Well, think about the actual constraints of a city. There's only so much land that you can build on, right? Cities have like a geographical barrier. There's only so many jobs that a city can have for people. There's resources that, food and water and, civil services and all these kinds of things like that are all finite. And there's probably not like an unlimited population size that a city could reach. There's probably some upper bound where eventually, yes, you can start building up vertically, like a New York City is very vertical, but that's really expensive also to do that. And you have to have like a really good economic reason to, to build vertically like that. For the most part, it's probably not a very realistic model to describe the population of something. In particular, in a biological sense, if you think about, say, the population of a virus in an organism, that's not going to grow infinitely. Eventually, the virus is going to kill whatever's in there, and then they can't reproduce anymore. Or if you live on an island, eventually the population will grow to the point where there's like no more food left for that organism on the island, and things will start starving, and the population really can't get any higher. So what we'd like is some kind of function that has like some built-in upper bound to it. Does that make sense? So what we're going to have is the logistic function. Okay. So we have the logistic function. We have two versions of it. We have c over 1 plus a times b to the x. And then we have c over 1 plus a e to the negative kx. Notice the negative sign is part of the formula there. Okay, notice that the criteria for the B's is opposite that for exponential growth and decay, but the criteria for the K's is the same. That often confuses students. I want to point that out. The reason that is the case is because there's that negative sign built into the version with the E in it. So the logistic function is nice because what's going on here is we have two horizontal asymptotes. One at 0 and the other at C. So what's going on here is that we're going to have a function that kind of looks like this. So a growth one would look this way, and a decay one would look like that. But it kind of grows exponentially in the middle, but then like levels off at the upper and lower bound. So again, this y equals 0 is like your lower bound. And your y equals c is like your upper bound. And sometimes we refer to that upper bound as the limit to growth. So let's look at a couple of examples using this logistic function to kind of get a handle on that, because this is brand new for us, right? We didn't talk about this last year. Okay. So it says to find the y-intercept, and then the equations for the horizontal asymptotes, and to graph the thing on the calculator. I'm going to do all the graphing at the end. We're going to do all the algebraic parts here that I have to write down, so I'm just not toggling back and forth between calculator and screen all the time. Is that cool with you guys? So to get the y-intercept, all y-intercepts have the same x-coordinate. What is the x-coordinate of a y-intercept? Zero. So I just would do f of 0. Now 0.6 to the 0 is 1, 3 times 1 is 3, 1 plus 3 is 4, so this really just turns into 10 over 4, or 2.5. Everybody's cool with that? The horizontal asymptotes are always going to be y equals 0 and y equals c. C in this case is 10, the numerator. So that's easy enough. As an aside, is this guy growth or decay? Is this logistic growth or logistic decay? What do I need to look at? Yeah, I need to look at that. And this is growth, since the b value is between 0 and 1. If I look at the second equation, the y-intercept there is going to be (31 over 5) or 6.2. Again, the horizontal asymptotes are at 0 and 31. Very good. And then is this guy growth or decay? This one is also growth, because what is the value for k? K is 2, not negative 2. Why is it not negative 2? The negative sign is part of the formula. Yeah. I wanted to make sure I hammer that because it tricks students all the time. Jack? So we have to be looking at the K's, not the B's. Yep. Yep, because it's the E version, not the B version. Is that cool? Okay. Let's graph these on our calculator and just kind of take a look at what's going on. So to type these guys in, I'm going to do them both at the same time, just for the sake of doing it. And I'm definitely using that fancy fraction command because it's going to be a parentheses mess to get the parentheses all right on here. You guys cool with that? Remember how to get the E on your calculator? Press second and then the LN button, which is just a couple buttons up from the on key. Okay, so there's that. I'm going to reset my window. I'm just going to go -10 to 10 on the x-axis. And then for the y-axis, I know that the lower bound for each of them is 0. The biggest upper bound is 31, so I'll make those the min and max. And let's hit graph. So here's our first one, whose upper bound is 10. Notice it seems capped in there at 10. Here's my second growth one, whose upper bound is 31. Notice they're both increasing as they go from left to right. These are both growth. If you're ever in doubt, just look at the graph and you can tell growth or decay pretty easily just by looking at if it's increasing from left to right. Does that feel okay, guys? All right. Let's do one more example and we'll call it good for today. Sound good to you guys? I think that sounds good to me too. God bless you. Man, somebody was sniffing the pepper this morning. All right. So, the population of a city can be modeled using the logistic growth equation below, yada, 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 where P is the population in the city T years after 1950. At the beginning of what year will the city have 1 million people? Okay. So what are we looking to solve for? T, because we hear the phrase what year. So we'll be solving for T. So what are we going to have to plug in for P of T? The 1 million. Everybody cool? Okay. Well, calculator time, that seems to me. So into Y1, I'm going to type the 1 million. Into Y2, I'm going to type the other side of my equation. Well, I'm just typing this stuff in. As an aside, you guys, if you're taking an ACT or an equivalent kind of test here in the future, if you're ever unsure of how to solve something algebraically, this graphing method that we're doing right now is a perfectly legitimate way to solve a problem. If you're not sure how to solve it algebraically, you can just graph both sides and look for the intersection or intersections. There could be more than one. But if you're ever unsure how to solve something, like this is a great little tool to use. All right, I'm going to have to reset my window. So T is years after 1950, so I'm going to go 0 to, I don't know, 100. I'm not really sure. I don't have any data points along the way to give me an indication of how fast this is actually growing. So I'm just kind of taking a guess. I figure 100 years, though, is probably reasonable. Since this is a logistic growth, I know the minimum or the lower bound is at y equals 0. And the upper bound is at 1,425,397. I'm just going to type that as 1.5 million. And go by 100,000s. Okay. So let's go ahead and graph. There's my line at 1 million. Here's my logistic growth curve. I just got it in there before the end of the window. That's great. Let's find the intersection there. Second, trace, intersect command, enter, enter, enter. And I get about 79,002. Remember that T is, again, going to be years after 1950. So this is 79.02 years after 1950. But is that actually answering the question? What is the question actually asking? At the beginning of what year will the population have 1 million people? So the answer to that should be but really I need to round that up to 2030. Why do I have to round it up? Yeah, at the beginning of 2029, your population will be less than 1 million because I still have a little bit of decimal on that 79. So I have to round it up to the next full year. Grrr. So you guys see why I rounded it all the way up, even though it was like your standard rules of rounding would tell you to round down there. The context of the question was really being quite specific, so I had to make sure I rounded up there. We're going to stop here. At this point, you guys could do up through 16. That'll be the start of your problem set, but remember that's not due until the 1st of May, so no need to worry about that right now, unless you really want to worry about it. And then please stress yourself out about it to no ends. Dominic.
I thought it was funny. I just put it in my calculator to figure out how far into the year